welcome to the next episode of the Klingberg Wing Mark II development. I'm Raul Klingberg, your host. And as you can see here, I have the structure for the right wing essentially complete. And after this little video here, I'm going to be putting it in storage and moving on to the left wing. But I thought before I do that, let's take a look at the work that's been completed recently and tell you a little bit more about it. So here we go. Let's see, I thought we'd start here at the root end. We'll talk about the flap. The flap itself is designed to go full 90 degrees like that. And for transport, it actually will fold up underneath. Originally, I was going to use composite Kevlar hinges for the flap, but I've decided instead to just use the Oratex covering material for the hinge and see how that works out. If that doesn't work out, I can go to something more mechanical. But all of the mechanical hinges involved having to put in reinforcements, rivets, bonding, and the fabric hinge actually might be superior in many ways. There's no fasteners, it's lighter weight, it's lower in cost, it's much less complex, it can be removed and replaced. So there's a bunch of advantages to it. Probably its biggest advantage is really high tear resistance, and the loads are distributed. Any other type of hinge, the loads get concentrated at certain spots, and with this ultralight structure, this is really not something we want. So the flap folds up underneath for transportation, and it makes the wing just a little bit narrower, 2-3 inches narrower. So that requires that I have a control horn that's removable here. And what I've set up here, the control horn for the flap is actually an 1/8 inch thick light ply with 2 layers of carbon fiber on either side, 6 ounce. And I found these button fasteners here. And let me pull this over in the shade, it'll photograph a little bit better. These are used for body panels on race cars and motorcycles, and they attach to a ball fitting. And you see that fitting here inside this hole, and it just pops on there. There's a little gripper that goes around it like this and holds onto that ball. And this is good for 150 pounds of tension this way, which is very high. And as you can see, there's a couple of holes here for pins. There'll be pins permanently mounted in the control horn, and they will take the loads of deflecting the flap. And the spring-loaded button keeper is really just intended for fastening and unfastening. I didn't want to have anything that required tools to install this control horn. So the control horn comes off for transportation, stays attached to its cable down here, and it'll just be stored on the pilot's cage somewhere. Use a piece of Velcro to store it. So I'm not overly thrilled with this fastener yet. I might go change to Zeus fasteners later, but I thought this would be interesting to try out, because you just push a button and off it comes. Now, you might be wondering what would happen if this came disconnected in flight for some reason, that little push button fitting fails or something like that, although these are highly reliable items. These 2 pins that go in these holes are quite long. They go fairly deep inside, and there's structure that's right here. So even if it did back off like this, those pins are still engaged, and the control horn would stay in place. It would be sloppy, but you'd still have flap control. And you really can't remove the control horn until you've disconnected the main wing panel here. You have to take the whole main wing panel off the center section in order to access this and slide it off enough so that you can disengage it. So fail-safe system, can't come off in flight. Let's take a look. We got a little pull cable here for putting the flap up and down, and that connects into a little fitting on the upper surface here on the inside. I'll put up a little photo of that. And of course, this has to be disconnected for transportation because we're going to fold the flap up underneath. And there'll be a little spring-loaded stainless steel clamp here that basically runs on the inside. This cable will run forward to a spring or a bungee that attaches to this fitting up here, puts the loads into the skin there. So there'll be a little spring fitting there. I gotta make the hole bigger here, a little different arrangement. I changed the design. So when when you push the flap all the way down past vertical, you'll be able to access that fitting and disconnect it and fold up the flap, and the fitting will just spring back inside. There will be a little retrieval cord attached to it, so that on the next assembly you just pull the cord and pull it back out, hook it back up again. I think that'll work out reasonably well. Let's see, what else should I tell you here about the flap? Let's see, I have set up here a piece of wood that simulates the upper skin. Of course, the upper skin's not in yet uh, because I have to leave it open to install the control cables, and I cannot install the control cables until I'm all rigged up with the center section and have the pilot's cage in the proper position. So in the meantime, it remains open. I put this piece of wood here to demonstrate the upper skin. You'll see that I have it set up so that the skin extends past the rear spar, and there's a notch in the flap here. And so it goes up underneath the upper skin like that and seals off. So for the first 5 or so degrees of flap deflection, 5 to 10, that gap remains relatively sealed. We won't get any recirculating air inside. And then as you go deeper into the flaps, just like normal flaps, that gap will open up. I may choose to put a piece of Mylar across here to close that gap up for over a wider range. I don't know. Sometimes with those strips of Mylar, they end up sticking up more than they seal off and become a problem in and of themselves. Um, Let's see, also on the control surfaces, I've experimented with different sheeting. This is fiberglass sheeting. It's carbon fiber on the inside. And in some spots I'm using basswood. Let's see, I think I got a piece of basswood out here at this location. Basswood is quite strong. It doesn't really need any fiberglass or carbon fiber. It's kind of a toss-up on how I like it. There's probably more work to making the composite skins, to make the skins to start with, and they are lighter weight, so it's more work to do them, but they are lighter weight. However, when you get into a situation like this where you have to blend the surfaces together, well, you got to come back with what you see here, automotive body filler, and because you can't just sand the surface, it's just 3-ounce fiberglass on there, and you have no material to sand off, so you have to carefully fill it and smooth it out, and that's quite a bit of work there. The basswood is 3/32 of an inch thick in this case, just like the sheet here, and if the parts aren't lined up exactly, well, you can just sand the wood down a little bit thinner. The wood, however, is heavier. So on this wing, I did mostly the fiberglass skins like this in a variety of locations, and on the other wing, I might go more in these small areas here. I might just use basswood. It'll go quicker and maybe a little bit better. I suspect that the basswood probably be easier to repair also, although it's probably just about a push. Okay, so the ribs were all set up all at once on the spar and hot wired, and then I cut off the ribs to install the spars here. This spar, fiberglass and Kevlar with carbon fiber cap strips. This spar is just, the shear web is fiberglass and Kevlar, and then the spar caps here are a combination of basswood and carbon fiber. Here on the inside you can see I put unidirectional carbon fiber on the basswood, and then they're spliced together. And if you look out here, every so often I have a 1/16 inch sheet of basswood running vertical as additional shear web. That was to add some torsional stiffness to the flap. It was a little soft in torsion, still might be. When I put the fabric on here, that'll help stiffen it up considerably, and if for some reason that's not enough, I can always open it up and go back and put in more of those strips to stiffen it up torsionally. So the flap is very light, it's under 2 pounds, and very strong. While we're here at this end, I thought I'd show you the cable guide. What I'm using for cable guides here, this is going to go in the ribs. It is a piece of 1/4 inch ID fiberglass tubing, pultruded, inexpensive stuff. And inside I have some 1/4 inch OD polyethylene tubing. And as you know, polyethylene is very difficult to glue to, next to impossible. But I discovered that if you sand it with like 80 grit first on the surface and put a couple of dots of CA glue on it and then slide it quickly into the fiberglass tube, it's really glued in there. You cannot get those out. So this provides a very smooth run for the cables, and they're very lightweight. And then on either side of the rib here, these are going to slide over, these little plywood discs, they're 64th inch thick plywood, will slide over the cable guide and glue to the rib like this to distribute the loads. So I'll have an extra large hole cut in the rib here that's about half the size of that disc, and that will allow me to position the cable guides so that the cable runs straight, and then glue that in place, and there's one on each side. And that's what's going to hold these cable guides into the ribs and distribute the loads. The fun part of these is, what do we have to make, like 48 of these. So I got some family members to do some work there on those and get those done. Let's see, what else do I need to show you here before we move on to other stuff. As you can see here, I changed the design a little. If you're familiar with the design, it used to have the flap running out to the Elevon, and there was so much stuff that I needed to accommodate in terms of the controls that I decided to take one rib bay and just provide a rigid zone, a lift zone, if you will. This is part where you can grab the wing and handle it, and it houses all of the various components needed for the controls. So I shortened the Elevon by one rib bay, which is not a lot. I shortened it here at the root end, not a big deal. The Elevon is still 10 feet long, so we have plenty of Elevon, and that provided a zone here for putting in the various controls that are needed. When I flip this over, we'll take a look at the bell crank on the other side. So once again, I did this skin as fiberglass on the outside, carbon fiber on the inside, 2 ounce on the inside, 3 ounce on the outside. And there's a molding error here, as you can see. It's got the measles. I had a lot of divots in that skin, and rather than throw it away and make another one, I decided to just go ahead and use it and put filler on there and smooth it out that way. It's not really any significant added weight. It's just more labor. So mistakes happen. I added a single layer of carbon fiber here. I keep strips of this stuff pre-cured laying around. It's about 1.5 inches wide, and this is glued to the rib. It's bonded very firmly to the rib, and the rib, you'll see, has carbon fiber face on it. And I added these caps on the rib so that I can carry the loads from the wing skins here into this wing skin, because they're not all one piece. And the reason they're not all one piece is because this is about as big a piece of foam as you can deal with, and it just was more convenient this way. Plus, it was a change in the design. Originally, the composite skins were going to end here, but I needed to do one more bay, so I needed to transfer the loads from the inner ones to the outer ones, and that's done via this cap on the rib. Now, there's actually 2 of these ribs that are carbon fiber. There's one here, there's one on the other side. Don't know if you can see it. Yeah, I think we can see that in there. And they carry the loads. They transfer the loads from the flap and from the Elevon up into the spar. So those are 2 structural ribs. Here in the center section, the flap loads are transferred up into the spar via the wing skins themselves. The ribs are essentially non-structural. They're just there as formers for the wing skins. Okay, out here in the outer wing, we have, I have the Elevon disconnected right now so I can show you some of its features. Control horn is permanently bonded on at this end. I don't know if you can see that with the horrible lighting that we have here today. Maybe you can see that. There we go. That stays on there all the time. The Elevon was constructed by cutting it loose from the ribs. I literally came in with a compass and marked the circle on the ribs, like here, and cut them out with an X-Acto knife, and I did that at every rib, and then I built up the spars. The spar here on the Elevon is 3/32 of an inch basswood right here, and it's set at a fairly steep angle because we got to do the bull nose on the Elevon. This is a ball and socket type joint for aerodynamic efficiency, and the inside of the spar caps are unidirectional carbon fiber, and the outside is just the basswood. But then I came in with 1/64 inch thick plywood. See if I can tilt this up for you here, and formed the bullnose this way by wrapping this around the foam front of the ribs. And I'll put up a couple of stills here to show you the internal structure in this. And these sections were essentially, this is longer than you can get the plywood. The sections were taped together, glued, wrapped, glued on one spar, cure it, then do the wrap and glue to the other spar. And there's foam pieces inside to provide additional support. And then before that bullnose was put on, I put in shear webs here. This is 1/64 inch thick plywood that is glued to the front face of the lower and upper spar caps. So essentially what you have here is a kind of an odd yet very functional D-tube. The spars are actually aft of the shear web, which is a little unusual, but it works. And the plywood forms the D part of the D-tube, and that gives this Elevon its torsional and bending stiffness that it needs. Now, the ribs in the outer panel, because the outer panel and the Elevon are covered in fabric, the ribs have 3/32 of an inch basswood cap strips. And if you know from the other videos, there's a little strip of plywood underneath this cap strip that runs on the rib, bonded to the rib, and it engages this spar cap and the rib cap strip. So that plywood strip that's underneath here, 1/64 inch thick plywood, carries the loads from the spar. The rear spar loads are carried into the spar caps, or excuse me, the rib caps via those little plywood strips. And there's one top and bottom. And if we look very close here, we can barely see the edge of that one there on the lower surface. And you can see here that I finished off the ends of the ribs with just a little bit of epoxy that I brushed on there to seal those off. And the front of the rib caps bond directly onto the spar flange. So that's how we get the loads up there. Rear spar, front spar, we get the loads back and forth via these cap strips. Once again, the ribs are non-structural. They are strictly there to hold the shape of the wing. And the Elevon's done the same way, except the trailing edge is a composite trailing edge. I did that, actually, even though it was more work, I did it to save weight. If I made the trailing edge entirely out of basswood or something else, it'd be too heavy. The trailing edge is, let's see, what did I do? That is 3-ounce fiberglass on the outside, and it's 4-ounce carbon fiber on the inside. And then in between, there's foam in here. There's Divinycell foam that provides a shear web between those, and that really forms a triangular shaped D-tube essentially in the trailing edge. Very stiff, very, very stiff, light, very strong. You see I'm doing more filling work here to smooth it out. The strips of basswood are only 24 inches long, so they have to be spliced. I laid up the unidirectional carbon fiber on full sheets and then slit them into strips, and the inside of the splice is joined up with another piece of 16th inch thick basswood that goes over the top of the splice. It's a diagonal splice, of course, and then that's a doubler on it, and then the plywood on the outside forms the doubler for the outside of the splice. And then the splices are staggered. In other words, this splice here and then the other splices somewhere else. They're not lined up with each other, just for added strength and structural integrity. So one of the more interesting features on this system is this center hinge. I needed 3 hinge points for the Elevon because it's 10 feet long. It wasn't quite stiff enough with just the ends supported. So I have this third one here. And what this is this is a permanently mounted piece of carbon fiber tubing bonded to the shear web here, fiberglassed in place, and the loads are carried up into the spar caps. And it is a slip fit with another piece of carbon fiber tubing that's 1/2 inch diameter that slips inside of this. So this is 2 pieces, 2 pieces, and there's another piece that goes all the way across inside, like that. And then bonded into that is this smaller piece of carbon fiber tubing. So you can see how it allows this piece of tubing to rotate up and down, and that becomes your hinge. And this shaft here slides into a fitting that's in the rib here at this location, if you can see that. There's a piece of tubing that I fiberglassed to the rib here. It's glassed on both sides. I cut the hole extra large to give me tolerances to work with, and once I get it all aligned, then I slip in some balsa shims and tack glue it in place, and then I fiberglass it to really hold it in place. And you can't see it here, it's hidden by epoxy, but there's a vertical piece of tubing in here also, a very small piece of tubing on the vertical right here. And this fitting here, this shaft, slides in to that piece of tubing right there, just slides right in, and this pin is not normally removed. Right there, that's out, slides in, and then that vertical piece of tubing I was showing you is a guide for this piece of piano wire that slides up that guide and engages this little hole here. And the horizontal tube in the rib and this hole line up. You slide the pin in other words, from underneath, and let's see if we can see it. No, it's going to be too hard to see that. So it goes right through the cap strip of the rib and follows that tube and goes right into this hole and the other hole, and that's what engages this hinge pin into the wing. And then the 90-degree bend here just simply gets taped to the bottom of the wing. There's some great outdoor vinyl tape, very durable, and nominally the Elevon is not removed. It stays on all the time, but in case we have to remove it for repairs, we can pull that tape off, pull this pin out, and then we can remove the Elevon. So slick little system. I stole this basic kind of hinging design from the radio control model airplane world and just enlarged it for ultralight aircraft, and I think it's going to work out quite nicely. It's all hidden inside, and nothing sticks out, so very low drag. Now the rib where that hinge pin is, it has to be structural, it has to carry loads because of that hinge pin. So this rib has carbon fiber on the inside of the basswood here to strengthen it, and then the fiberglass puts the loads from the hinging system into that carbon fiber that's on those rib cap strips and transfers it up to the spar, front spar, and back to the rear spar. So this is actually a highly structural rib. It's really, really strong. The rear spar is constructed of multiple layers, actually. I used 1/32 inch plywood on the outside, aircraft plywood, and then on the inside 1/16 inch basswood that was staggered aft slightly and then sanded so that I have the appropriate shape to match up with the bull nose that's on the D-tube of the Elevon, and that helps seal this up. I think I might still slip in some of that furry window seal stuff to finish sealing this gap, but this worked out quite well. The seams in the basswood are doubled up with 1/64 inch plywood here on the inside, and then it's glassed. Every rib bay has fiberglass here and up in here to create a very strong spar. And you see I used the 1/64 inch plywood as the shear web also. And it will be springy like this, that's okay. There's not a lot of structural loads in this, and it should carry the loads without any problem. It's mostly aerodynamic fairing. It provides a housing for the bullnose to run in and stay sealed off. I found that with the bullnose on this Elevon that this has to be 1 inch deep in order to provide enough room for the bullnose. Let's see what else we got on the Elevon. I should talk about the fitting for the tip. Inside both ends of the Elevon are carbon fiber tubes like this that have a mating tube that slides inside that it runs on. Runs really, really smooth. And out here at the rib is a fitting right here where the tube can be inserted this way, goes into the tube that's here, and when the winglet mount is in place, it stops that tube from going out that way. Inside this tube here is a stop, so the pin cannot go further that way, and it can't go the other way because this guy's in the way. If I ever need to take the Elevon off, of course when this is removed for transportation, I can reach in with a little pair of needle nose pliers, and I can reach inside here where the tube would be and grab a hold of a little handle and slide the tube out using the needle nose pliers. So this is practically identical to what's at the root end. So I have two tube and tube hinges here at either end, and essentially the same thing in the middle. And each one has a methodology for removing those pins if I ever need to remove the Elevon for maintenance. Here at the root end of the Elevon, you can see the tube that slides in to provide the pivot point for the Elevon. And this gets secured on the inside with a cotter key, and there's an access panel in the lower surface to get to it. We'll take a look at that later when I flip it over. You'll notice that where these hinge points are, I've put a couple extra layers of doublers on the ribs, both here at the root end and at the tip end, to carry those loads that come from the hinges. So what I was doing out here today, the reason I have it out today was to just put these two fittings on here. There's one on the upper surface here, one on the lower surface, that help align the main wing panel with the winglet mount and allow me to do the finish sanding here on the front. So this winglet mount, a little bit more filling on it, some fine filler and sanding, and I should be able to get it covered tonight or tomorrow. So that part will be done. The wingtip panels are obviously done. You've seen those before. The winglet's not here because it's not needed, but it's done. So ostensibly, the structure for the main wing panel is complete, except for the final skins after the controls are hooked up. So we'll do the little flip around here, and I'll be back in a minute, and I will show you the lower surface of the wing. We'll take a look inside at part of the control system. Okay, we're back here. We're looking at the wing on the sawhorses upside down. And I thought this is a good time to show you a little trick I did with the Elevon to solve a earlier problem. If you've been following along, you know that this wing panel doesn't have quite enough washout in it, nor does the other one. Both wing panels are off by about 1.5 degrees in terms of the amount of washout. And I've been noodling around about how I was going to solve that problem without building new wing panels. And the solution came to me when I was cutting out the Elevon. As I cut it out, I realized, because of the reverse taper in the Elevon, it's wider at the tip, there's actually quite a bit of area out at the tip, and that constitutes a significant portion of the cord of the airfoil, about 30%, 35%. You see from the hinge pin here to the trailing edge. So what I did is when I glued on the 64th inch thick plywood to make the bull nose of the D-tube on the Elevon, I had a jig set up here on this tip rib, and that jig had alignment to create 2 degrees of washout in the Elevon itself. And that's why you're seeing, if you visualize the cord line for this airfoil, you're going to see a little kink in it. It's lined up at the root end down there, which you can barely see, but here at the tip, it's actually angled up slightly. So there's 2 degrees of twist in the Elevon. And I figured 2 degrees of twist of about 35% of the cord would make up for the 1.5 degrees that I'm missing, or make up for most of it. So it was an easy fix. No major rebuilding or anything like that. Just build a little bit of twist into the Elevon. So essentially the airfoils, as you come out towards the tip, the airfoils get a little bit of reflex in them, and that solves the washout problem. Now, that'll have a minor impact on the high-speed end of the flying capability. It'll reduce performance slightly because it's going to offload the tips and push the load more towards the center, but probably no more so than the extra washout. Except in terms of creating the washout effect this way, it's a little less efficient in terms of the induced drag that's caused, the lack of efficiency in the airfoil due to the reflex in it. So it's a trade-off. We save the wing panels and we sacrifice just a tiny skosh of performance. And I think it'll fly just fine this way. This solves the need for that added washout. And sometimes you don't realize how to fix these things until you're in the middle of building it. You know, I could have probably sat there and looked at it for months, done it on a computer, and it just would not have dawned on me. But as soon as I was building the Elevon and saw how flexible it was, and looked at the shape, and all of a sudden this little light bulb went on, and I went, oh, I'll just build some twist into the Elevon, and that'll solve my problem. And I hope it does. I hope it works. So let's go take a look at the bay down here where the controls and so forth are. Well, first I should show you the root end of the Elevon. We need to carry some significant loads here. So the upper skin has 2-ounce carbon fiber on the inside, but on the lower surface I just have a small amount of basswood sheeting here to keep the ribs stiff when I put the covering material on. But this will carry the loads and up into the spar. That'll handle those just fine. I did the same thing out at the tip to transfer the loads from these skins into the hinge point that's out there. So within this rigid bay in the middle, we see here the fitting that holds the pin. This is the pin that can slide in and out. It's a little sticky right now. It's heated up. But this pin will slide all the way in, and there's a cotter key that goes in here. Cotter key actually comes from underneath, slides up through here, and you bend it over, and the cotter key will secure this pin and make sure that it can't go further in or further out. There will be an access hole here in the skin that I can just cover up with tape, and then I can always take the tape off and get in here and pull the cotter key out if I need to remove the Elevon. Let's see, what else should I show you? Here's the bell crank. The bell crank's made the same way as the control horns. See if I can get it into an area of better lighting here, more even lighting. It is 1/8 inch thick light ply with 2 or 3 layers of carbon fiber on either side, and there's a carbon fiber tube that is mounted, bonded in the middle here, and you see I got some nice fillets of structural adhesive there to hold that straight and tight. And inside this section, I'll zoom in close to help the lighting some. This box here is quite stout. This is 3/16 inch thick foam, 2 layers of 6-ounce carbon fiber on both sides. This is a really stiff box, and the loads are carried into the carbon fiber skin here and into the rib and into the spar. And this will take the loads that are on the bell crank due to the controls. It rides on this 1/2 inch diameter carbon fiber shaft, and there's a stop down here. It doesn't just sit on the epoxy. There's actually a little piece of tubing here that's slipped over it and bonded in place, and it's also bonded from the other side, and it's glassed off on the inside, glassed off on the outside. This is, the whole wing could be destroyed, and this will probably still exist. They're just fine. And then this bell crank slips over. There's a cap that goes on this, like that, to hold it in place so it doesn't come loose, and a cotter key goes through to hold it in place. And there'll be another access panel here so that I can get in to work on this if need be. So that's the bell crank. Nice carbon fiber fittings, always self-lubricating. And I'll come back in a minute and I will show you the push rod setup for the controls here. So now you can see how the push rod assembly will go in here. It's pretty much a standard push rod. It has rod end fittings on it that have these nice ball joints to allow for odd rotation and motions. This piece of carbon fiber tubing that happens to slip nicely inside these fittings. These were custom fittings that were made for another glider project, and a friend of mine donated them to the cause here, which was very nice. Thanks, Bob, for that. And of course they have reverse threads. One has a right hand thread, one has a left hand thread, so you can screw the push rod one way to trim the Elevon up, screw it the other way to trim the Elevon down. There'll be a slot here in the wing skin where the push rod can traverse. It goes both back and forth this way, and there's a little bit of side-to-side motion because I was a lazy designer and I didn't bother aligning, doing perfect alignment on the control horns. So as this goes up and down, that control horn travels on an odd arc, causing the push rod to have a swinging arc like this. But we'll just make a slot wide enough for that to run in, and I might put some furry stuff in that slot to close it off aerodynamically, but still allow the push rod to move side to side as it needs. But these ball end fittings are great. Aluminum housings. These get bonded onto the carbon fiber tube, and then one little cherry rivet goes in just to be a belt and suspenders, and we're good to go. I didn't mention earlier, the little thimbles here are set up and ready for the aircraft cables. I'm using 16th inch diameter 7x7, no actually, yeah, 7x7 cable as control cables. you might think 1/16 of an inch is too small, but actually that's good up to more than 600 pounds. I think ultimate it's about 800 pounds. And if there's ever 600 pounds of pull on one of those cables, I got problems that are much bigger than that cable failing. Something else has failed terribly way before then. So that gives you a view. Oh, I didn't talk about the rear spar because I had not planned on having this rigid middle section here, this one rib bay uh, for housing all this stuff. I hadn't planned on a rear spar here, and I had to build it in place. So what I did is I just took some of the spar cap material that I used on the main spar, and that is, they're long strips. They reach from about here to here. Well, let's see, if you get that in shot, they reach from here to here. And there's a shear web of half-inch thick foam with carbon fiber face sheets, and then these pull-truded carbon fiber strips, cap strips, carry all the loads, and get them transferred into the skins because I glassed it. Used some fiberglass here to glass it on the skins. I'll sand this when I put on this lower skin and get a good bond here. And then I transferred the loads up here via the shear web and the cap strips into that spar, and same kind of deal on the inside here. So I just essentially built a spar in place, and that'll work just fine. And that's about it for now. I think you've had a good view of the wing. Let me see, walk back around this other way. We'll take a look at it from the other direction. I did weigh it and added the amounts for fabric and missing panels and so forth. And right now the half wing with the winglet and everything else will weigh 38 pounds. And I was hoping for 35, so I'm a little over. 38 times 2, and then add the center section of pilot's cage, and I'm sitting at 108 pounds. So I think it's fair to say that we'll come in at about 110 pounds for the entire aircraft, minus the emergency parachute and minus the aerodynamic fairing for the cockpit. But in terms of bare weight, which is how most of these aircraft are measured, we're at about 108 pounds, 108 to 110 currently. And I was shooting for 100, so I call that close enough. If you can stay within 10% of your goal weight, it's been a good design. It's been a lot of work. It's been a lot of sticks and twigs building, as you can see. Composites are heavy. They're extremely strong, but they are also heavy. And in order to keep the weight down here, I had to do some very traditional sticks and twigs type building, which means oodles of parts. Lots and lots of parts to be cut out and glued together. But it really does keep the weight down. And wood's an amazing material, keeps a very high strength weight ratio, and it's very easy to work with. It's just a lot of fiddly work, and you have to be a decent builder to work with it. It's not like you're just gluing together molded sections. So there we go. I appreciate you watching, and if you want complete technical details and you're a YouTube viewer, what you want to do is you want to click on that link to my Patreon site and go over there and throw your hat in the ring, so to speak, and get access to all of the building logs that I post, where you get more technical details and you see the incremental movement as I go along here. It took me about 3 months to complete the structure on the right wing because a lot of it was not designed, and I had to design as I went, which stretches out the process. As I stand there scratching my head, not knowing what I'm going to do next for a while. So the right wing should go a lot faster. I expect to complete the right wing in about 1 month. Excuse me, the left wing. I'll complete the left wing in about 1 month, maybe 5 weeks. And then there will be the setting up of the controls, which will take 2-3 weeks. So somewhere in the December time frame, we'll be looking at hauling this out for initial ground testing. And if we're lucky, we might get a short hop in yet this year. And for now, I'll sign off and I'll go set up the left wing on the bench and get back to work. And I'll be back to talk to you guys sometime in the future. Thanks for watching. Bye for now. Fly safe.